So, last time we talked about one of the most important properties of metals, namely the electrical conductivity and arrived at a very interesting relationship known as the Drude relation, which gives the electrical conductivity sigma as n E square tau by m, where n is the electron concentration, E is the charge, and m the mass of electron, and then tau is the so called relaxation time, which determines how the electron gas relaxes after a scattering or collision event back to the equilibrium configuration. So, this tau describes the process of relaxation, the characteristic exponential relaxation. It is the time constant of this exponential relaxation process. Now, obviously, E and m are constants, and the electron concentration in a metal is a constant more or less for a metal, because it depends on the atomic number and the Avogadro number and the not the atomic number, but the atomic weight and the Avogadro number and the density. So, this is practically a constant. So, all these are constants. So, the conductivity is mainly determined by the temperature dependence of the electrical conductivity, mainly depends on the temperature dependence of this relaxation time. So, we all know, for example, if you consider a material like platinum, platinum is very well known as a resistance thermometer, and we know that it is preferred as a resistance thermometer because it can be available in a very pure form, and also its resistance is strictly proportional to the absolute temperature. So, it is a linear function of the temperature. So, that is the more or less very to very high degree of accuracy, it is a linear function of the temperature. So, its calibration from the resistance, conversion of the resistance to a temperature is all fairly straightforward and universal, and this is the reason why platinum thermometer, this is preferred by all over the world as a resistance thermometer. Now, this characteristic linear temperature dependence of the electrical conductivity or the electrical resistance, this is got by the temperature dependence of sigma, and which is entirely determined by the temperature dependence of the relaxation time. And we already saw that the collision processes or the scattering events for conduction electrons arise mainly from two principal mechanisms. The scattering is from impurities of various kinds, lattice impurities, interstitials, vacancies, dislocations, all sorts of standard defects in crystalline solids. So, that is one mechanism. The other mechanism is scattering by thermal vibrations, which we wrote as the quantized excitations of thermal vibrations were written as by the name phonons. We will talk about them a little later. Now, these are the two principal mechanisms, and the defect scattering is not very strongly dependent on the temperature in comparison to the temperature dependence of the thermal vibrations. So, the phonon scattering is very strongly influenced, and the linear temperature dependence of the electrical resistance of a pure metal arises principally from the linear the temperature dependence or the relaxation time of for the scattering by phonons, scattering of electron gas by phonons. We will see about the details of this after we have discussed the nature of phonons and so on. So, we will postpone the discussion. We will be satisfied at this stage with the description of the Drude relation. We will return this a little later to the specific application of electron phonon scattering process and how it determines the temperature dependence of the electrical conductivity of a metal. We will take up this topic a little later. Now, we will pass on to another important and interesting characteristic of a metal, namely thermal conductivity. We all know that a good metal is not only a very good conductor of electricity, but also a very good conductor of heat. So, that is why we are unable to hold a metallic rod which is being heated at one end, even if the rod is a very long one, because the heat is conducted down the metal and it heats up our hand. So, we know at the same time we also know this depends to a great extent on the type of metal. For example, stainless steel does not conduct heat as much as a copper rod, for example, or a brass rod. So, there is a strong variation of the thermal conductivity. So, we would like to understand this also in the framework of the free electron theory of metals. So, we all know the standard equation for the thermal conduction. It is got by the standard Fourier equation for steady state heat conduction as minus K A dt by dx, where dt by dx is the temperature gradient and A is the cross section, and K is the thermal conductivity. K is the thermal conductivity. So, this is the temperature gradient. We all know that the heat flows against a temperature gradient. So, from a hot end to a cold end, whereas the gradient is directed from the cold end to the hot end. The negative sign is an indication of that. This is the heat current, or heat quantity of heat flowing per second. And this is the area of cross section, A is the area of cross section. So, this is the standard heat conduction equation. We would now like to know how this thermal conductivity is determined by the transport of heat by the electron gas. In order to understand this, we go back to the kinetic theory of gases. We are talking about an electron gas, but we will still try to keep the classical picture and go to the kinetic theory, which describes how heat is transported in an ideal gas. This is done by if you have a heat gradient, a temperature gradient from say the gradient is like this, so that there is a hot end, let us say this is the z direction, this is the cold end, and so there will be a temperature gradient dt by dz. Suppose we consider a section here and look at unit area, and in this unit area, if there are n gas molecules or atoms per unit volume, then on an average n by 3 of this will be directed along the z direction, because x, y and z, there are 3 standard directions in 3-dimensional space, and if there are n molecules, by perfect randomness of the kinetic theory allows us to assume that on an average 1/3 of these molecules will be flowing along the z direction. So, of which half of them will be travelling down and half of them will be travelling up. So, on an average 1,6N will be the concentration, and they will be confined to if you consider unit area and V is the speed, 1,6NV will be the number of gas molecules which are incident from top to bottom crossing unit area. So, this number, and if we consider the temperature thermal transport, the transport of heat across this unit area, then the transport of heat is determined by the molecules which suffered a collision before the instant we are talking about. So, from this unit area, if L is the mean free path, L is the mean free path. So, just before one collision, before they cross, the instant that the molecules cross this unit area at the in the central section of the z axis, if we consider that those molecules would have to travel a distance L in order to reach, only those molecules will transport heat from the hot end to this unit area. So, we will have, if I take the temperature in this section as T, temperature is the absolute temperature. So, this means a Taylor expansion says T minus dT by dz into L will be the actual temperature of the molecule which starts from the previous collision and it which reaches in unit time to this by travelling this. So, this times this gives you the energy transported. So, energy transported across unit area per second. Of course, this is heat energy from above, and which contributes to this heat at this point at a given instant of time, that will be given by 1,6NV times T minus dT by dz times L. So, that would be the, this is the, this energy will be proportional to this, and correspondingly there will be also molecules travelling from below, and that section which will come will correspond to So, we start from this expression for the kinetic theory expression for the thermal conductivity. The next important question is that since we are talking about a finite temperature, not at absolute 0, we are talking about heat transport at a finite temperature well above the absolute temperature. So, we would like to have an expression for the electronic heat capacity at a finite temperature, whereas we have talked about it only close to the absolute 0. So, let us spend a little time calculating this extra, the electronic heat capacity exactly. So, the electronic specific heat C electronic. How do you calculate it at a finite temperature? In order to do that, we start from the internal energy, which is a function of temperature, and that is by according to the standard this thing, this is a standard definition, this is an integral, the average of T of E F of E times E divided by dE T of E f of E from 0 to infinity. So, that would be the statistical average of the internal energy, and we also know that we have the n times E f, that would be E f times the electron concentration, which is just d of E f of E dE. So, this is the concentration of the electrons. So, now we take these two, we know that the electronic heat capacity or specific heat is just got by differentiating the average internal energy with respect to temperature. So, this by looking at this is going to be integral to infinity, and differentiating this we get, since this is a constant number. So, this is going to give me, this is E f into dN by dt, and that will be just E f integral dE dFE dF by dE. Okay. So, taking these two together, we can write an expression for the electronic heat capacity C electronics as integral dE E minus EF times dFE dF by dE. Now, since we know that this will vary only slowly in the neighborhood of the Fermi energy, we can regard this density of states dFE is the density of states, which may be regarded as a slowly varying function in the neighborhood, slowly varying in the neighborhood of EF. Therefore, because of that, we can take this out of the integral and replace it by its value at the Fermi energy dFEF, so that we can write C electronics as dFEF times integral 0 to infinity E minus EF dF naught by dE times dE, where F naught is the equilibrium Fermi Dirac distribution function, and we know its form is F naught 1 by exponential E minus EF by kB T plus 1. So, we can differentiate this and get the electronic heat capacity. So, we arrive at C electronic as d of EF times, if we replace this integral 0 to infinity E minus EF times, I differentiate this, I get exponential E minus EF by kBT plus 1 square with a negative sign, and then I have exponential E minus EF by kBT upstairs in the numerator, and then minus 1 by kBT square to do the differentiation to 1 by kBT. So, that would give you the electronic heat capacity coefficient, and plugging all this, and let us make a substitution, E minus E f by k B T equal to x. So, that we finally arrive at the expression C electronic as k square d f E f the states there are completely occupied, do not contribute anything to the integral. So, we may change this to just 0, and then this is a standard integral which has the value pi square by 3. So, this will be a definite integral whose value is known to be pi square by 3. So, we arrive at the final expression for the electronic heat capacity So, that is the exact expression for the electronic heat capacity coefficient at any temperature, and so this is the value of the linear heat capacity coefficient gamma, which we wrote last time. So, this is the expression for the electronic heat capacity which we should import into the expression, kinetic theory expression for the thermal conductivity, and that is how we finally arrive at the thermal conductivity of the electron gas. So, doing this, so we have C electronic is gamma T, where gamma we have seen now as pi square k B square by 3 into d f f. So, using this expression, we can go back to the thermal conductivity expression, and we can see in particular what happens to the ratio of the thermal to the electrical conductivity, and we will write k by sigma T. This is a very interesting constant which turns out to have this value. This is because we know the Drude expression sigma equal to n e square tau by m, and therefore, we have the kinetic theory expression for the conductivity in which the mean free path can be written as V tau. So, that is how, simplifying this, we arrive at this very interesting expression which is valid for the electron gas, free electron gas in metals in general, which is a very interesting relationship which is known as Wiedemann-Franz law. It gives you a very interesting fact that if you take the ratio of the thermal conductivity to the electrical conductivity for any material and divide by also the absolute temperature, you arrive at a universal constant, because this involves only the Boltzmann constant, the factor pi, and then the electronic charge. So, this constant is a universal constant known as the Lorentz number. So, this quantity k by sigma T turns out to be a universal constant whose value is the standard Lorentz number. So, this has been actually experimentally observed in many metals at low temperatures. Of course, there are interesting deviations which arise from the limitation of the relaxation time approximation. We will talk about it later. Now, all I want to say is at this point that, well, one can say that one started from the kinetic theory expression for the thermal conductivity, which is a classical description, whereas we have the usual objection that the electron gas is a quantum assembly and therefore subject to quantum or Fermi-Dirac statistics, subject to Pauli exclusion principle. If this is so, one can arrive at the same thing via the Boltzmann transport equation. instead of starting from the kinetic theory, we can go back as we did in the case of the conduction electrons, the electrical conductivity problem. We can go on to the Boltzmann transport equation, in which we will now write, instead of an electric field which drives the electrons, we now have a temperature gradient. So, we will write dF by dt as field as del f dot V, and this del f can be written as, so this is V dot dF by dt times dt by dx, say along a standard direction, or del t. So, we can relate, this will be a minus sign to show that the drift of the electrons is against the temperature gradient, and this will give you, this is balanced by the dF by dt due to collisions or scattering, which has the standard form f minus f naught by tau. Now, using this, we can express the distribution function in terms of the equilibrium distribution function and the other parameters involving the temperature gradient, and the knowing the standard behavior of the kind of Fermi-Dirac distribution, we can arrive at the same expression for the thermal conductivity, and in turn to the, we can come back to the Wiedemann-Franz law. Before concluding this lecture, I would like to spend a little time on another interesting effect which is very well known in metals, namely the phenomenon of thermoelectricity. Thermoelectricity means, we all know, we have all heard of thermocouples, which are formed by a junction formed by two dissimilar metals, and then if this junction is kept, if I have a pair of identical junctions and if they are kept at different temperatures and there is a temperature gradient, then there will be an EMF generated. So, this is the phenomenon which includes both thermal transport in the presence of an electrical field or vice versa, an electric EMF induced by a temperature gradient. So, in order to describe it, the absolute thermal power is defined by pi equal to Ts, where S is the absolute thermal power, thermoelectric power. It is also known as the Seebeck coefficient, and pi is the so called Peltier coefficient. So, this is, and T is the absolute temperature, of course. So, this is the standard expression which links the Peltier effect and the thermoelectric power. In the Peltier effect, we are interested in the heat given out or taken in at a junction between the conductor of interest and a reference material such as a superconductor, which makes no contribution to the thermoelectric power. If you take this, and if the ith electron carries a thermal energy Hi is the thermal energy Now, what does that mean? So, if the Hi is the thermal energy of the ith electron, then Hi times Vi of x sigma over I is the x component, Vix is the velocity of the x component. So, this is the heat current. So, if we take this and if we have also an electric current Jx, then the electric current due to electrons flowing is simply given by sigma I E V I of x. So, that is the electric current J x flowing in the same direction. The Peltier coefficient pi is just the ratio of the heat current to the electric current, and therefore, we can write this as sigma H I V I of x by sigma E V I of x. And here H I is the energy which we can write as E minus E f, E I minus E f, where E I is the energy of the ith electron. So, putting all this together, we get the thermo power. So, we have the thermo power as 1 by E T sigma E I minus E f times V I f x. This can also be rewritten using the definition of J, the current density, and in this way we can replace the summation by an integration over all the energies. Now, we already have discussed how to obtain the electrical current due to the transport of electrons. So, we just borrow the expression from that, and we can write T s therefore as 1 by E t. Borrowing all these expressions, we get integral E minus E f and then sigma of E into tau V x square divided by sigma x d f by d. So, now again we have converted it into an integration over the energies, and we know that this makes an appreciable contribution only over a range of energies of the order of kBt in the neighborhood of E f. Therefore, we can again use a Taylor expansion in the neighborhood of the Fermi energy and calculate this, and the final result turns out to be a very compact expression. So, the final result for the thermo power of a metal, going to the algebra, we get a very particularly compact expression pi square by 3 kb square by E d sigma of E by dE by sigma of E, and this can be rewritten as so, the thermo power of a metal is again proportional to the linear function of the absolute temperature, and then it mainly depends on the logarithmic derivative of the thermal electrical conductivity. Now, the electrical conductivity, as we know, is given by the Drude expression Ne square tau by m, and therefore, the energy dependence of these factors is not very strong. The strongest energy dependence comes from this, which is the energy dependence of the DFE, the electronic density of states at the Fermi level. So, this is the main factor determining the value of the thermoelectric power in a metal. So, we have now seen how we can combine all the three transport properties, namely the electrical conductivity, the thermal conductivity and the thermoelectric power can be all explained in the framework of the semi-classical, so called semi-classical theory due to the electron, free electron gas. Later on we will also discuss effects of an applied magnetic field. So, and this will give rise to interesting effects like the Pauli paramagnetic susceptibility, and the entire theory of free electrons in metals is vindicated by the observation of phenomena such as thermionic emission, photoelectric emission, field emission, etc. And so, we can talk about the topology of the Fermi surface from experiments such as cyclotron resonance, de Haas-Van effect and things like that. So, we will discuss all these at a later stage to go into the details of the of these interesting physical behavior. For the moment, this in fact, this is also the Fermi surface, the electron, the Fermi energy of an electron moving close to the surface of a metal gives you an image potential, which also provides the basis for the so called field ion microscope. So, these are interesting developments in experimental solid state research. We will just I am mentioning it in passing, and we now move on to the discussion of other classes of solids.